Hello everybody, I want to talk today a little bit more about acids and bases with emphasis on diprotic and polyprotic acids in general. So these would be acids. Let's just take a case of diprotic is sufficient for the conversation because you really get the gist of polyprotic beyond that. Let's take the case of, I'm going to get, I'll wipe this a little better here. Let's take the case of an acid H2A. I'm going to write it in a general form. It has, you can think of it having two equivalents of protons in there. And so in water, this will give us on the first step HA minus aqueous and H3O plus, step one. And step two, we go on with the HA minus, if you like to write it like that. I'll give you a particular example in a second. And water, now the fact of the matter is these both have Ka. So let's take an example. This would be like vitamin C. You can look up the structure of it on your own. That's a common nutrition associated weak acid. Now the Ka values, let's take vitamin C, between the steps are usually significantly different. The first being usually several orders of magnitude larger, and I have to look up the values. This is something I don't keep in memory. This is beyond roughly page 21 in the notes. Ka1 for the first step, products over reactants, I'm just putting a subscript 1, is 9.1 times 10 to the minus 5, and Ka2 for the second step here is a lot smaller. It's 1.6 times 10 to the minus 12. So let's just say hypothetically we would start out with a system that was 0.100 molar in H2A, vitamin C. Go through the ice table method, and this is going to be minus X, and you're going to have an X and X here. We're going to ignore the second step. So you could solve for hydronium ion concentration simply by Ka1 is 9.1 times 10 to the minus 5 is equal to X squared over 0.100 minus X, and solve it out. You could do it quadratically, or in this case, try a small x approximation where smaller than 10 to the minus 4, barely, and see how it works for you. And you can always check to see if you're within 5%. If not, do it out quadratically. They're both straightforward methods. You do not get any significant benefit to the number of sig figs that you're working with here by using something with 10 to the minus 12. There's a trace amount of this. It's for something where you're coming in with 3 sig figs or so, inconsequential for your calculations. It's going to be way under 1%. So that's the first case. Now there is a significant exception, and it is significant, so we're going to go through it because this is a chemical we use in the lab all the time, and that's sulfuric acid. Sulfuric acid is a diprotic acid. A diprotic acid. So technically, I guess diprotic or polyprotic. Some people consider them two different things. A common polyprotic acid with more than 2 titratable protons is, I'll write, phosphoric acid has 3 equivalents of protons or hydronium ions associated with it. But even with that, the first step is much larger than the second step, and the second step is much larger than the third. So you can estimate the acidity of this from the equilibrium with Ka1. And so, but with sulfuric acid is a little different. That's H2SO4. You should know that. That's important molecule, important acid. Use it in the lab. It's found in nature, it's a component of acid rain. It's in car batteries. It's in a host of things you deal with. So in water, I write it out the longer way. I like doing that. The first step goes 100% to hydrogen sulfate, that anion, and H3O+. 100%. Step 1. Step 2, no. The hydrogen sulfate goes on aqueous. And that step has equilibrium with the sulfate ion and H3O plus. That's an equilibrium step. Let me get another marker really quick. I'm dying here. So we have this step here. This has got no equilibrium constant. We don't write an equilibrium constant for this because it's a strong acid. You will, like I said, you can look them up. They're done in other mediums besides water to determine that, but in water, it's effectively going 100% to the right. Here, Ka, I'll just write it as Ka because it's going to only be one Ka value, is 0.013. Let me verify that, 0.013. It's small, it's a weak acid, but it's not that small of a number. That's not negligible. So, if you wanted a very crude calculation, you could just treat it as a strong acid and ignore the second step, but we want to be a little more sophisticated than that. So we have to account for both protons if we want to do this correctly. So let's do it out. So let's say I'm going to work a problem here. Let's say we have a 0.0500 molar. It's part of a skill builder. There's more to it. Molar solution of this acid, right? So that means on the first step, we're going to pick up 0.0500 molar H3O plus on step 1. This is from step 1. So that's kind of a good point. We also are picking up, that will go into our goal, of course, is to get pH. The second thing to note is that because it's all 1-to-1, that we're also picking up 0.0500 molar of the hydrogen sulfate ion, right? So what you do next is you set up an ice method here. It's kind of like, it is doing ice. So what you do is you say initial here is 0.0500, right? We ignore the water. There was no sulfate, that's a big 0, but there's a little difference here. Let's take a look. So we have that, but we have also, what do we have here? We have 0.0500 molar, this is all in molarity, of the hydronium ion that exists from the prior step, right? So that's important. So on the change step, we have a minus X. Oh, we pick up a plus X over here. Everything's 1-to-1, a plus X. At equilibrium, 0.0500 minus X, 0.0500 plus X. We have that. So what you do is set this up. Ka is 0.013, and that's equal to, we're right at the products of reactants. It's got the sulfate, it's got H3O plus, it's got HSO4 minus, right? Products of reactants, ignore the water. Now we plug in. It's going to have an X, a 0.0500 plus X, and we're going to have that, and then in the bottom we're going to have the same number minus X. On this one, there's no easy way. You cannot use the small x approximation because the Ka value is too large. It's on the order 10 to the minus 2. So you're going to end up with a quadratic form of x1 and 2 roots, if you will. in the form, well, you're going to end up with that. Let me just write, what I'm going to do is I'm going to set you up. This problem's worked out in the worked out notes. You have x squared plus 0.063x minus 6.54 times 10. I'm going to put it as a dot here because we got a lot of things that look like x's. Times 10 to the minus 4. That's going to be our equal 0. That's our polynomial equation. When you solve it out, x is equal to the realistic root 0.00902. Solve this out yourself. The big mistake here is people don't add. When you're doing the pH, you have to add the total. That's going to be the hydronium ion concentration. You have to add total H3O plus is equal to that number plus the 0.0500 molar from step 1. So that's important. And so the number ends up being 0.05900 molar of the hydronium ion. So it's not the same. It's not trivially different. So the final step, of course, is getting the pH, and the pH is going to be equal to the negative log of 0.05900, and that ends up being 1.23. As you expect, it's very acidic. If it's not very acidic with sulfuric acid, you've made a big mistake. This wraps up application of the Bronsted theory. I'm going to make a final video on what Lewis acids bases are for those of you going on to other forms of chemistry. This was the bulk of the material right here. The Bronsted-Lowry type applications will go on to the next chapter. So at that note, that will kind of be a standoffish video. On that note, I'm done. Have a good day. Take care.